Hello students, welcome to my channel JD Physical Science class. Now I am starting a new playlist where I am going to solve some good exam ready problems from standards books. So in this, continuing this, let us solve first problem from Zettili book. So the chapter is 4, exercises 4.27. So here they have given you a particle of mass m, which is confined to move in infinite potential box, where at the center of the box you have a delta potential. Now they're saying find the particle wave function corresponding to even solution when E is greater than 0, and find the energy levels corresponding to even solution. So let us understand the problem. So you have a potential barrier. So there is a no point to solve it for E less than 0 because there is a no bound state. So we are only going to solve for E greater than 0. And since now the potential is here symmetric. So potential is symmetric. So the wave function solution will be of definite parity. Either they will be even or they will be odd. So now first we are going to see the even parity wave function. So now say if I want to write the solution for this equation, so you see inside the box here there is a rigid walls, so potential particle cannot escape here. So here the wave function is 0, and here you have potential V0. So V0 particle is free. So Schrodinger equations for V0, and when energy is positive, it is like a simple harmonic motion. So this you have a solution like A sine kx plus B cos kx. But here we have to show continuity of wave function at x is equal to 0 also. So we will take and because I am solving for even function, so I am taking the solution of this equation as A cos kx minus B sin kx between minus A to 0, and A cos kx plus B sin kx from 0 to A. If you want, you can take the here A coefficient with sign. Generally, when we do A with sign, so if you want, you can take A with sign, but I am taking it for A with cos x, so it will not affect our solution. So these are my solution, and now you can see as sign whenever sign is sign minus x is equal to minus sin x, so it's automatically become plus. So if I draw this function, so this function is even with respect to the middle of the box. So if you so your minus kx become plus. So this is the even solution of this equation. Now we want to find the value of A and B. For that, we can apply the boundary condition. So let us see at the position of so this wave function combined together can be also written like this. B sin kx, B sin kx. You can also write A sin kx and B cos kx. Whatever way you want to write, you can write. And now say continuity. So psi should be continuous at x is equal to 0. So this gives me size 0 value A. So this gives me size 0 value A. Now, if I apply first derivative is discontinued at delta potential. So this is the condition we have done many times. This is the condition of delta potential, discontinuity at the delta potential. First derivative is discontinued by this amount. And now here, so we have psi x we have already defined. We can differentiate, we can find the psi dash x, and now I can find psi dash 0 using the wave function at 0 after the delta function, and similarly I can find psi minus 0 just using this wave function just before the delta potential. So that means left of the this is left of the potential barrier. This is the right of the delta potential barrier. So I can use this function what we have defined, and I can differentiate. I can put I put x is equal to 0. So and I will solve this one. This gives me putting these values. This gives me 2 bk. K where k is 2 under 2 me upon x square. So this gives me a relation between A and B. So either I can remove B or I can remove A. I can write B. No, I can if I want to remove A, then I can write in terms of B. So whatever way you can write you can write the solutions. So now this becomes now this is my wave function, and now A I can take common. So B, so here was A and B become A beta. Here B become is the beta, so A beta. So in this way I can write. So if I want I can replace B also. So here A also, here I have replaced B with A. So these are the wave function. This is the first part. So this is the wave function for even solution, even parity solution for this problem. Now I want to find the energies. So in order to find the energies, I can use either continuity wave function at x is equal to minus a, or continue or x is equal to a. So and accordingly I will use this wave function. So now I'm using at x equal to a. So x is equal to a, I can use the wave function right of the this delta function, and psi a should be 0 because there is a rigid walls. So putting this one, now this gives me the condition, and this gives me the energy condition 10k minus h cut square k upon mv0. So this is the final. By solving this equation, I can find the energy of the particle. So this equation can be solved using a graphical method. So if I solve this equation using, if I find the k, I can find the energy. So if you solve this by graphical method, the k value comes slightly greater than n pi by 2. Okay, the k will become slightly greater than n pi by 2. That means now the energies are greater than the infinite potential wall of 2a length. So if I take infinite potential, the energy levels will be n pi square 2h square 2m. A is here 2a. So energy level will be in the case here will be greater than the infinite potential box. Now suppose if I take, and this is my equation, so I'm plotting minus h cut square k mb0 with and 10k. So now if I say this v0 is 0, so if I take v0 0, then this become infinite, and this line, if I if v tends to 0, this line will become steeper and steeper. So this line will go slope will keep on increasing. Slope will keep on increasing this side, and the solution now k solution will be now exactly n pi by 2. So when I say v tends to 0, that means now there is a no potential delta potential barrier, because we are putting v0 now. That means this is simple box. Now this is a simple box, and you get the energy level exactly equal to k equal to n pi by 2, which is the energy levels of a infinite potential box of length 2a. So if you v0, this becomes simple box. Now what happens if I take v naught is infinite? So if I take v naught infinite, and slope will be keep on decreasing, and now k, and now this will point will touch here. Solution will be k equal to n pi. So k equal to n, when I put a k equal to n pi, then simply what will happen now? Now this, when the potential barrier in the delta function potential barrier become infinite, now these become two boxes. So this one two boxes. Now the energy will be simply n square pi square square 2ma square. That means this energy will be now simply of a box, in a square infinite box of length a. So 2a, a, sorry, a. So this will be now en will be n square. Because I'm now taking not 2, so n square pi square square. These are the allowed energy of the infinite square well of width a. So now so here, so this is now what this become 2 4a square. So 2 and 2 2a is a length. So this way, So if V0, so V0 means you don't have any potential barrier in the middle of the box, and V infinite, but it means now this box become in two parts. Okay, two isolated infinite box becomes. So this is important question for exam. Generally, they cannot ask you to solve the graphical in the exam, but they can ask this expression in the exam. So this is important question for the exam. So hope I will come with some more new questions. So I'm stopping here. Thank you very much.